Welcome everybody, this is Tom Stephan with Goulds Water Technology, and today we're going to talk about a magnetic contactor control box. So we're going to look at the control box, we're going to discuss all the components, we are going to go through the checkout procedure, and the other thing that we're going to do is we're going to do the checkout procedure with an analog meter and a digital multimeter, just to cover the differences in terms of meters. So we've taken the cover off of this control box, and we can see that there is a wiring diagram as well as a checkout procedure. So we don't really need any other form of documentation, but just as a reminder, that same information in terms of the checkout procedure and the wiring diagram is in what we call the main manual, and that's the Motor Application and Installation Data Manual. Let's talk about some of the components. The example we're going to use today is a CB30412MC. So that is a control box, 3 horsepower, 4-inch motor, single phase, 3-wire of course. With a control box we're talking about a 3-wire and single phase. And the 2 is 230 volt. Now the MC stands for magnetic contactor. So we can see some of those same pieces of data laid out here, 3 horsepower, 230 volt, and there is an amperage rating. Notice we have amperage rating, in this case 14.5, and then a service factor max amp rating of 17. So we always want to make sure that the control box can handle the service factor amps of the motor itself. Some other information here, you got some date code information, and we can see it is a NEMA 3R, so a type 3R, NEMA 3R enclosure, and it gives some explanation here, acceptable for indoor or outdoor. 3R is outdoor and it's rain tight, so we can put this outside. Some more electrical data, single phase, 60 hertz, service factor of 1.15, and a kilowatt value. So let's take a look at some of the components here in the control box. So again, with a control box, we're talking about single phase coming in, single phase motor. And so if we start here, these are overloads. And in this particular case here, with your 3 horse, you have 2 overloads. One on the start and one on the main. And so here's our terminal block. And so if we just kind of turn this up a little bit, so we've got some labeling here, and so we'll talk about this. One of the common questions is, how do I wire a pressure switch? So we'll talk about that. That's what this terminal is for. Line 1, line 2, so that's your input power coming in. So we know it has to be single phase 230. And yellow, black, red, and those are the colors of the motor. So that's my output. So I've got a switch terminal, input power 230, and then output to the motor, which is pretty typical with electrical components. We see the input power on the left and the output to the motor on the right. Let's look at some of the components here. This is the magnetic contactor. And so we've got a magnetic contactor, which is really just a switch. Down here is the relay. Again, it's another form of a switch. And we have 2 capacitors. Essentially, you have a start capacitor and a run capacitor. This is really just a cap start, cap run box, which is capacitor start, capacitor run, with a magnetic contactor switch. So those are the components. Let's take a closer look here at some of the wiring and how some of these components work. This is again a magnetic contactor, a mag contactor box, and again this is our mag contactor. So again, the mag contactor is really just a switch. And the interesting thing about a magnetic contactor is the two terminals on the side are the coil. So when that coil is energized, it allows that contactor, that switch, to close. And so now current, electricity, can flow from the input and make its way to the output. So one of the most common questions with these types of boxes is, how do I wire up a switch? So again, if you look at the back side of that cover, it will show you how to wire up a pressure switch. So really what we're talking about is a standard pressure switch. And really that's the beauty, one of the big advantages, of a magnetic contactor, that allows us to use a standard pressure switch, just a standard regular pressure switch, right? Something like this, as opposed to, what we commonly call a heavy-duty pressure switch, right? So with the mag contactor, we can use a standard pressure switch. And one of the common questions is, how do I wire up that pressure switch? So if you look at the manual, it tells you that one terminal of the pressure switch, right, one side, we can use either the left side or the right side, really doesn't matter. So on one side of that switch, we're going to go to the SW, and on the other side, it's going to go to L2. So we only need one side of the switch, and we only need two wires. So I think the interesting thing is, we can see that, might be a little tough for you to see, but that switch is going directly up here, and that's the, let's just call it the right side of the coil. And on the left side, we can see that it is jumped. So, and this is power coming in, right? And so because it's jumped, we always have power on the left-hand side. And because this is connected to your switch, right, when that switch closes, right, you've got power to the right side of the coil. And when you have power across the coil, that allows current to flow. That switch closes, right? So that is how everything is wired, and how you wire up the pressure switch, and how that works with a coil in a mag contactor. The coil side is lower current than the other side. So that's how and why we can use a standard pressure switch. Some other components here. The white box it's really another switch. It's a relay. Typically, relays are used for lower current compared to a magnetic contactor, but it's simply just another switch. The two capacitors that we have, there is a start capacitor, and then there is a run capacitor. Now, the 3-horse is a little bit unique. One thing is, we can see that the terminals, now I've taken the bracket off so we can just show you, we can take a look at how they're wired and some of the labels on there. So one thing that's unique about this 3 horsepower is the terminals are facing down, right? Doesn't really make a huge difference, but that's one thing that's different. And the other thing is, sometimes the diagram that you're looking up in the book or on the back of the cover doesn't exactly match the orientation, right? So in this case, this is the run capacitor on the right. The start capacitor is on the left. So one thing we have to be a little bit careful in just comparing our diagram to what we actually see. All right, so we have, again, just like a cap start, cap run box, we have a start capacitor and a run capacitor. With the 3-horse control box, mag contactor control box, we have two overloads. The one on the left is called the main overload, and then the one on the right is the start overload. So a couple unique things about an overload that's in a control box versus in the windings of the motor. Really two main things. One is we can test them, and we can replace them. And so we'll cover that process of how to test it. And the other thing here is there's a manual reset. So if they are tripped, we can manually reset those. So your overloads in the control boxes do have some advantages over the overloads that are in the windings of the motors. So what we're going to do now is we're going to follow the checkout procedure, which again, it's on the back side of the cover, and it's also in the MAID manual, that motor application installation data manual. But we're going to use two different meters just to show the difference between an analog meter, and we're going to use a Simpson 372, which is an ohm meter, and then we're going to use a multimeter, because there are some differences here, and we just want to sort of explore what it looks like with both meters. So we're going to start with A. And A is the overload, right? So we have two overloads. And we will start with the analog, the Simpson 372. So with a Simpson, it always says, you know, what scale. So in this case here, it's R times 1. So here's our scale. So we're going to set it to R times 1. We always want to zero it out. So we're going to put the leads together, and we're going to adjust our zero dial, and we want to just make sure that that lines up there. All right, so now that we've got it zeroed out, not a bad idea to just double check it, right? Okay, so we've got it zeroed out. All right, so now we're going to test the overloads. And so if you look at the overloads here, again, we got two overloads, right? A main overload, a start overload. And in this case here, we only have two terminals each. We're going to put our leads on the two terminals. And sometimes it gets a little tricky. All right, so we just want to get that on there properly. Right, and that looks good. And what should we be? So as we look this up on the back of the cover or the MAID, it says that it should not be over 0.5 ohms. So in this case, R times 1, we're looking at the top scale. And yes, we are not over 0.5 ohms. So you would want to do the other overload, right? But that testing is exactly the same. So let's switch to the digital multimeter. With our digital, in this case, we are using a Fluke 1587 digital multimeter, and we're measuring ohms. So we got to just make sure that two things are correct. One is the leads, so we can see we've got ohms over here, and then the other is our dial. So we're going to move that over and measure ohms. So one thing that's sort of unique about this meter, we can see that we get an OL. An OL means that the leads are open. So one thing that we could double check, we could do the same thing. So we're going to put our leads together, and so what it's showing is, bounces around a little bit, it's showing that we've got around 0.3, 0.4 ohms of resistance just through the leads. So one thing that tends to trip us up a little bit with the digital multimeter is the fact that it's so sensitive, it's going to give you some sort of reading, right? And this particular meter does not zero out, right, like your Simpson. So if we're taking measurements that are really small, we want to do this and then subtract that value. All right, so let's do the same test. So we've got it on the same leads of the overload. Right, and we do have, again, some resistance from the leads themselves, and really nothing more than that. So again, that is less than 0.5. So, you know, we could kind of start to see some of the differences here. with the Simpson, I've got to change the scale. I got to zero it out. And then I've got to think about what scale I'm reading. And I probably have to do some math, right? So depending on the setting, and we'll see that. With the digital multimeter, it's auto scaling, which is one nice feature, and it automatically puts the units in there. So with a digital multimeter, we're just going to read from left to right, and we want to make sure that we're including the units. So in that case, that is A, and that's our overload. And again, we're going to test both overloads the same way. Just to make sure, though, we do want to make sure that we just press both buttons on the overload before we do that test. Step B is to test the capacitor. And so because capacitors, their job is to store energy and release energy when needed, there might be some energy still in the capacitor. So the common rule of thumb when checking a capacitor is to disconnect the leads and then discharge that. So we're just going to look at the run capacitor in this case because testing capacitors is the same methodology. All right, so we're just going to take these off. Before you do that, not a bad idea to take a picture so you know where all the terminals go. All right, so we're going to disconnect here, and it just in terms of discharging, it's just connecting, shorting those two terminals. Essentially what happens is if there is a charge in there already, then it's going to go through your meter, which could damage your meter. So more than likely, though, if they've been sitting around for a while, they've already discharged. All right, so first one we're going to do is the Simpson. So again, we have to set the scale. So in B, we're looking at R times 1,000. So there's our scale, R times 1,000. I'm going to connect our leads together, zero it out. Not extremely critical in this case, but we're going to zero it out. Now what we're going to do, we're going to put these together because this happens fairly quickly. We're going to touch these leads, and you're going to see the needle swing to the right and then back to the left. So we're just going to try that here. Fairly quick, right? It goes to the right and then back to the left. If, let's say, that we were distracted and we missed that, we can just reverse the leads, and we can see that again. All right, very quick. That is one way to test a capacitor. It's probably not the best because if you had a capacitor tester like this has, then you would actually read the specific microfarad rating. So every capacitor has a different microfarad rating. We can see here this is 45 microfarads plus or minus 5%. All right, so again, the beauty of the digital multimeter is it can do more than one thing. So again, the trick is let's make sure that we set up our digital multimeter correctly. And in this case here, we're going to move it over. It says ohms, but we want to get to the capacitor symbol here, which is in blue, and so we just need to hit the button. We can see that it changes the scale to, it's just showing nanofarads right here. But again, the beauty is it will automatically adjust the scale. So now we've got our meter set up properly. We're going to do the same thing across the terminals. And then we're just going to read this from left to right. So we got 45.4 microfarads. All right. So again, we double check. 45 microfarads plus or minus 5%. So test good. There's two tests we can do on our relay. So this white box here is a relay. Again, that's just a switch. And the first test is a relay coil test. That's C. in your literature. And then D is a relay contact. So let's do C. And what it tells us is we want to disconnect terminal 5. Again, it might be a little tough for you to see, but we have terminal 1, 2, and 5. So the first step is we're just going to disconnect 5. All right, so 5 is disconnected. And again, we're going to start with the Simpson. And the Simpson is R times 1,000. So R times 1,000, same procedure, right? Put your leads together, zero it out. All right, and now we're going to go between 2 and 5. So get my hands out of the way here. We got 2 and 5. All right, so R times 1,000. All right, so it looks like we've got about, here's 5, and there's 10. So each hash mark is 1,000. So it looks like it's between 6 and 7,000 ohms. And what is the spec? Between 4,500 and 7,000. So we're good because we are under that 7,000. Again, a little tricky because, you know, we have to think about what's our scale, R times 1,000 in this case, and we've got to do a little math and count our hash marks. But we're good, right, with this meter. So now let's do the same thing with the fluke. With our fluke, we've got to make sure our leads are correct. So we are measuring ohms here. Then we got to set our dial to ohms. All right, so now we're going to do that same test, 2 and 5. We're going to connect to 2, and we're going to connect to 5. We're going to leave it in the auto ranging mode so we can see 6.12 K ohms. So K is 1,000, so we get 6,120 or 30 ohms, which is good. Again, just another tool to use and some differences between the two. So let's move on to the second test that we can do for the relay, and that is the relay contact. Next test is D, if you're following the made manual or the inside cover, and that is our second test that we can do on the relay, and that is a relay contact. So in this case here, we have to disconnect the lead from terminal 1. So we're just going to pull that off. Again, we've moved this relay just so you can see it. So now we've disconnected terminal 1, and ohmmeter setting R times 1. We've got to follow that same procedure with our Simpson. Every time we change the scale, R times 1, we've got to zero it out. Because a lot of these values are very small, so we do need some accuracy here. All right, so we've got that zeroed out. And now we're going to go between terminal 1 and 2. So there's terminal 1, there's terminal 2, and the spec says 0. So we can see 0, so we're good there. And so now we're going to do the same test with the multimeter. Again, we have it still set at ohms. I'm going to do the same test, 1 and 2. All right, this is where it gets a little tricky, right? The spec is 0. Why are we showing 0.2? Well, because these are very sensitive and it's measuring the resistance of that short amount of lead, which in the beginning when we clipped the leads together, we were getting about 0.2. So we subtract that out and we're back to 0. So the last step, which is E, is the contactor, the magnetic contactor. And so we're going to measure the coil. And so this is the coil side. And the first thing that it says is disconnect one of the leads. So we're just going to disconnect the one on the right, which, by the way, is to your switch, right, SW. And just to make things a little bit easier to get my hands in here, I have removed the capacitors. You don't need to do that for the test. So again, we'll start with the Simpson 372. And the first thing that it says now is R times 100. So we've set it to R times 100. Always want to zero that out. So we're set there. And now we just want to go across that coil. We're just going to go across the coil using our alligator clips. All right, so here's where it gets a little tricky. So R times 100. And notice that this is a meter that is a little bit newer and it has some more scales on it. And notice the bottom here. Bottom scale is R times 10 and R times 100. So now we're looking at the bottom scale, and in our case, multiplying by 100. And it looks like it's, between 5 and 6, slightly over 5. Let's call it 5,500, right? 5.5 times 100, 550, right? And if we look at the spec, our spec says it should be between 180 and 1,400 ohms. So again, this is, I think, kind of shows that it gets a little tricky, making sure we read the right scale and multiply by the scale that we're on, in this case 100, so slightly over 500, let's say, or 550. We're going to do the same test with the digital multimeter, and remember, we've disconnected one side of the coil. We chose this side over here. We did remove the capacitors. We didn't have to for this test. It's just to get some stuff out of the way so you can see it clearly. And now we're going to use the multimeter. So same exact test, and we are going to dial that into measuring ohms. And I really haven't changed the leads. So we're going to go across the coil. And we can see here, again, this is in kiloohms, or 1,000 ohms, which is 0.864 or 864 ohms in this case. And again, that's within the spec, which was between 180 and 1,400. It's a little bit easier in terms of really letting the meter do the work for you. We just need to make sure that we are reading the units. All right, so 0.864 kiloohms or 864 ohms. Thanks for watching our video today. For additional information, go to Goulds.com.